Hi guys, so today we begin topic 11, which is energetics. And in this video, we will be introducing the topic of energetics, and we will also be explaining the difference between endothermic and exothermic reactions. So what exactly is energetics? Energetics is a branch of chemistry which studies the changes in energy during physical processes and chemical reactions. So we know that energy is the capacity to do work, and it exists in many forms. It exists in chemical, light, electrical, and most importantly, it exists as heat energy. So in most chemical and physical changes, there is an associated energy change. These energy changes exist in all chemical reactions. And in some cases, it's the energy change that is more useful than the products. Say, for example, we have the combustion of a fuel. The products of combustion are carbon dioxide and water. However, we don't really want those products. What we want is the energy change. That energy change is what we get as heat when we burn fuels. These energy changes take place between a system and its surroundings. So let's say, for example, we have a reaction taking place in a beaker, right? So whatever is happening inside the beaker and the solution is considered the system. The surroundings, which would be the table and the air around it, right? This is the surroundings. So heat can either be lost to the surroundings or it can be absorbed from the surroundings. So let's firstly look at endothermic reactions. When the head of a match is struck, energy is released. How is it released? It's released in the form of heat and light. Energy from the system, that's this is the system, is released and it heats up the surroundings. Another example can be when adding an acid to a base, the beaker may feel warm to the touch. So this is a very important definition to remember. An exothermic reaction releases energy to its surroundings, causing the surroundings to get hotter. So let's look at the word a little carefully now. Exo means to exit and thermic means heat. Heat exits, right? So that's one way to remember. The heat is always released from the system. Endothermic reactions. So just like how we have exothermic reactions, we have endothermic reactions, which is the exact opposite. Endo means to go in and thermic means heat. So in endothermic reactions, we have heat going in to the system from the environment, from the surroundings, right? So when you squeeze an instant cold pack, you know those, the ones that you get in the first aid kits, there's a squeeze together here sign. So this here contains a little pouch of water and outside of it has salt. So when you squeeze this, it releases the water and the water reacts with the salt and it instantly decreases the temperature, right? Energy from the surroundings, as you see here, is absorbed and it becomes cooler. An endothermic reaction absorbs energy from the surroundings, causing the surroundings to get colder. This is very popular with ammonium salts. These are some common examples of exothermic and endothermic reactions. Combustion reactions are like anything that requires burning. We have precipitation and displacement reactions, neutralization reactions, which include acids and bases. Endothermic reactions include the cracking of hydrocarbons. This is found in section B. You'll be seeing more of that soon. the melting of solids, evaporation of liquids, and dissolving ammonium salts in water. So let's consider the following reaction. We have hydrogen and oxygen gas reacting to form water. Now, naturally, these two compounds don't react with each other just like that to form water. You need to put in energy into the system in the form of heat. And what that heat does, it helps to break up these bonds to form new bonds in water. So, bond breaking absorbs energy. Anything which absorbs energy is considered endothermic. And the minimum of energy required is called the activation energy. So, as I just said, if there was no activation energy, if no heat was added to this reaction, water will not be formed. The particles then rearrange themselves and new bonds are formed. So, after these break up, they rearrange and they form their new bonds. And in that process, energy is released. So, bond forming is considered to be an exothermic reaction. Enthalpy. All substances are said to possess enthalpy, or also called heat content, and we refer to that as H. So, if a reaction is carried out at constant pressure and if no other work is involved, then that heat that is absorbed or evolved from the reaction is considered the enthalpy change. Right? This is the formal definition of enthalpy. Right? So the change in enthalpy, we put a delta sign in front of it. Delta H. Change in enthalpy. How is this measured? Enthalpy change is the difference between the energy of the products and the energy of the reactants. So if the energy of the products is more than that of the reactants, we will see that heat energy will be absorbed from the surroundings, the system becomes cold, the actual value of enthalpy change is positive, and then you can determine that the reaction is endothermic. However, if the enthalpy of the products is less than that of the reactants, the overall heat will be released to the surroundings. The system becomes hot and the physical value of enthalpy change will be positive, and that positive sign will tell you that the reaction is considered to be exothermic. So these changes in enthalpy can be better illustrated with an energy profile diagram, such as these, right? So these diagrams show you the enthalpy of reactants and products. That will be before and after the reaction. And it should also show the activation energy as well as the enthalpy change. So for an exothermic reaction, as the reaction progresses, this axis can also be labeled as progress of reaction or time, right? So as this reaction progresses, you see the change in enthalpy. So for exothermic reactions, it starts off with this value of enthalpy, right? It gains energy, activation energy, and then it loses a lot more than what it had before. So the change here, this loss of energy makes enthalpy change negative. A negative enthalpy change would mean that heat is released to the surroundings and the temperature of the system will increase. When we compare that to an endothermic reaction now, the reactants they have a lower enthalpy, they gain a lot of activation energy, and then when they release their energy, they form their products. So the overall enthalpy change for an endothermic reaction is positive. A positive enthalpy change will indicate that heat is absorbed from the surroundings to break those bonds, and therefore the temperature of the surroundings will decrease. You'll be asked quite often to draw energy profile diagrams, so you must know every single feature that you need to have. All right, so firstly, you start off with your axes, right? One must be labeled energy content. It can also be labeled as enthalpy. This is your y-axis. Your x-axis can be either course of reaction or reaction progress or time. Okay, so you always start off with your two lines, right? So actually first you need to determine whether or not it's an endothermic or an exothermic change. That will decide the shape of your graph. So if you look here, your exothermic reactions, your reactants are always higher than your products, whereas in an endothermic reaction, your reactants are lower than the products. So in this case, we have an exothermic reaction. Once we draw our straight lines for your products and your reactants, you then write your formulae for the reactants. You also write the formula for your products on this line, right? Always label your activation energy as well as your enthalpy change. And you must also include the value of the enthalpy change, and most importantly, that sign, that positive or negative sign. Yes, this is exothermic, so it is negative. However, for endothermic reactions, you must put the positive sign in front of this value here. So in our last topic, rates, we learned that a catalyst increases the rate of a reaction by giving the reactants a lower activation energy. All right, so in terms of energy, the catalyst provides an alternative pathway for the reaction which requires less activation energy than without a catalyst. So you have to think of it as these reactants, they have to climb a hill, right? They use more energy to reach the top of the hill without a catalyst. With the catalyst, they require less energy. The less energy it takes to climb that hill, that means the more reactants are able to have successful collisions with each other, and therefore they will react faster to form their products. How we show the effect of a catalyst on an energy profile diagram, we just draw a shorter line compared to the original activation energy. So once it's still connected to the reactants and products, and once the enthalpy change remains the same, it's just this very tiny change you need to make in the graph, right? So you always put the original graph without the catalyst, and you include the activation energy with the catalyst. Again, same thing for this one. This is without a catalyst, the red line, and the purple line is with a catalyst. So these questions are a quick check to see if you understand what was done in this video. Be sure to pause the video at this point, or you can download the document that I'll be sending you for this video. Make sure you're able to answer them, and I have the solutions in another slide, so you can check over to see if you got everything correct or where you went wrong. And this is your assignment. So you're going to classify each of the following as exothermic or endothermic, and you're going to draw energy profile diagrams for each, and this has to be uploaded as an assignment on Edmodo page, right? So I just want to see 3 diagrams with everything here labeled on the diagram. So that's it for today. Our next class will be a live session explaining how we calculate different types of enthalpy changes. That's it for today. Bye.